Hey guys, so last class I had you investigate a little bit about some of the properties that affect gases. So you used the simulator to explore pressure, temperature, and volume. And hopefully what you found out from that activity was that if you change pressure, volume also changes. If you change the temperature, then the pressure will change. And then if you change the temperature, you can also change the volume as well. From that exploration activity, I'd hope that you could see that all of these things are really interconnected with each other. It's cool to know that if you heat up a gas, it'll expand and explode. It's interesting to find out that pressure will decrease as temperature decreases, but more importantly, it's helpful to be able to quantify these things. Using something called the combined gas law, we can actually quantitatively predict just how those values will change if we start to alter them. So the combined gas law should appear on my screen here that you guys can see right over here. And it says that P1 V1 over T1 is equal to P2 V2 over T2. So here's our opportunity to do a little math and a little calculation in order to quantitatively determine or predict some properties of gases. Now, the only trick here is that pressure and volume have to be in the same unit on both sides, and temperature has to be in the unit Kelvin, which we talked about really early in the beginning of the school year. So let's just practice a little bit. So here's a question. It says, a sample of hydrogen gas has a volume of 65 liters, a pressure of 0.992 atm, and a temperature of 338 Kelvin. What will the volume of the hydrogen be at 0.984 atm and 298 Kelvin? So if we start to change things like pressure and temperature, how does the volume change? This kind of stuff's important if you work in engineering, because you need to make sure that the size of your container is correct depending on what will happen to that container as it ships or transports across the country or to a whole new place. So the first step in figuring these out is, well, what do we know? So step one is going to be, what do we know? And in this case, we have to look and say, well, do we know the first pressure? Do we know the first volume? Do we know the first temperature? Do we know the second pressure, the second volume, and the second temperature? So let's take a look. It says that a sample of hydrogen gas has a volume of 65 liters. So that's going to be our first volume. Now I know it's the first volume because that unit, liters, is a unit for volume. We also know the pressure, the initial pressure is 0.992 atm. And again, I know that is the pressure because of the unit being used, atmospheres. And then lastly, we know the first temperature. It's 338 Kelvin. And I also know that because Kelvin is a unit for temperature. Now, what else do we know? We know the second pressure is 0.984 atm. And we know that the second temperature is 298 Kelvin. Which leads us to step two of our problem solving. What are we looking for? And in this case, the only thing that is missing is the volume. So we're trying to determine what the second volume will be. And in order to solve for the unknown, we have to do a little math and use that equation that we were given at the beginning. So the equation says that our P1 times our V1 over our T1 is going to be equal to our P2 times our V2 over our T2. Okay? So let's start plugging in some of the things we figured out before. So we figured out that our first pressure was 0.992 atm. We figured out that our first volume was 65 liters. We figured out that our temperature was 338 Kelvin. We were looking to find out the second pressure. We were looking, and we know the second pressure was 0.984. We know the second temperature is 298, and we don't know the second volume. And now, in order to solve for this missing piece, this volume, we have to cross multiply and then solve for that volume. So we'll have 298 times 0.992 times 65 equals 338 times 0.984 times V2. And now we need a calculator. So here goes our calculator, right? So we'll say, okay, 298 times 0.992 times 65 equals 19215.04 equals 338 times 0.984 times, is 332.59 times V2. And in order to solve for V2, we have to divide both sides by 332.59. That'll cancel out, and we'll find out that our V2 is equal to 19,215.04 divided by, this is Niemo got crazy. 19,215. There we go. Divided by 332.59 equals, oh my gosh, what is happening right now, guys? Okay, ready? Technical difficulties. 19,215.04. There we go. Divided by 332.59 equals 57.77 liters. So what we found out there is that our second volume would be 57.77 liters if we made those changes. So the volume would decrease from the original volume of 65 down to 57.77 liters. Okay? Now the tricky part for these is not solving for the unknown. I think that it's making sure we go through and find all of the different pieces. Now, you might find out that once in a while, one of these properties of a gas is actually held constant. And so let's talk about what happens if that is the occasion. So what happens if if something is actually held constant? So here's this example. I'm right down here at the bottom of this handout. And what happens if one of our variables or one of our properties doesn't change at all? What do we do in that case? So it actually makes the problems a lot more simple if something is held constant or is actually just missing from the problem altogether. So let's take a look at this example. So this example says if I have 17 milliliters of a gas under pressure at 88.89 atm, what will the pressure of the gas be if I leave the temperature constant but decrease the volume to 12? So the steps are the same. We're going to first go through and make sure we know what we know. So do we know the first pressure? In this case, the first pressure is 88.89 atm. Do we know the first volume? And it says that the first volume here is 17 milliliters. Do we know the first temperature? And it says they leave the temperature constant, so this is sort of missing. We don't know what that is. Okay, let's look for the second pressure. The second pressure says it's going to be, well, that's what we're looking for. It says what will be the pressure, so we don't know that. Do we know the volume? It's 12 for the second part. And then lastly, that second temperature, again, it says these are constant. So the nice thing is when something is constant like that, we can just leave it completely out. We don't even have to put it in our formula anymore. We can just figure out pressure and volume. And so we'll say, okay, well, if P1 times V1 equals P2 times V2. And in this case, then we're just going to go ahead and solve for that. So P1 was 88.89 times our V1, which was 17, is going to be equal to our P2, which we don't know, times our second volume, which we do. And in order to solve for that, we just divide both sides by 12. It's going to cancel out on this side. And here we go to my crazy calculator skills. And we'll try it again. So it says, okay, 88.89 times 17 divided by 12. And what we would find out is that if we decrease the volume, then our pressure is going to increase. So our final pressure is going to go up from 88.89 to 125.93 ATM. Just for reference, that's 125 times the pressure you feel right now on Earth. That'd be crazy. Okay, so those are some examples. Thanks for tuning in. Take some notes into your notebook on this information, and next class I'm going to give you an opportunity and some time to practice these kind of calculations, and then the class following that you'll have a quiz on this information. So take some time to ask me some questions, to post some questions in the comments on Classroom or via Hangouts while you're watching this video, so that I can get back to you with anything you're still not sure about. Okay, I'll see you guys soon. Miss you lots. Bye.